right, thanks Kyle for the introduction. How are we on voice up there? All good? All right, you can all hear me? So yeah, thanks for the invitation to come down here and present some of the work that myself and some of my group have been working on the last 4 or 5 years on really thinking about how we can repurpose some of the ocean bottom node seismometers that are put on the seafloor, you know, to do some interesting things, observe some interesting wave field phenomena that maybe we haven't been looking at previously. So this is not just a solo effort. This is actually a number of people that have contributed to this, in particular, Aaron Gerard, who was my PhD student at University of Western Australia, now, I guess, postdoc at Mines, and then research associate for Mines, just lead Mines. But he's been instrumental in a lot of this. This has also been a strong industry collaboration with Bjorn Olofsson, Mike Danalushkin, Simon Herfitson, and Karsten Udengard at various companies sort of down in Houston. And really, we're looking at seismology on large nodal arrays. So just so that we're all on the same page in terms of what sort of goes on in some modern acquisition, so in the last 10, 15 years, ocean bottom nodes have really come to the forefront in being an industry standard for doing types of seismic acquisition. So on the right-hand side, we have a remote operated vehicle coming up from a support ship that goes and deploys these instruments on the sea floor. So see there's about 20 of them here. I'll show you sort of 2 slides up from now, sort of what the actual distribution would look like in a regular experiment. But the idea is that once they're in place and all turned on, they're continuously recording. And then if you have a source vessel, which then sails up over top of it using air guns, which is just compressed air, setting off a large sort of exciting an explosion, I guess, in the water. This energy then, of course, propagates down through the sediment, back up, and is recorded on these OBNs. And the idea is that by doing almost like a Zamboni on an ice rink, you go all the way around this area, and then you basically have excellent coverage that you can do some interesting seismic experiments. So what are these nodes that are actually put on the seafloor? So they're about yay big. They weigh 20 or 30 pounds. They have battery life that lasts for up to 100 days. And they have 4 components of recording. So there's one in the water that's a hydrophone that basically is a pressure sensor. And then like a sort of a seismology, a seismograph, you would have sort of 3 components of ground shaking. You'd have your vertical and 2 horizontal components. So those 4 components basically make one of these OBNs. And these have sensors that have sort of around 4 to 14 hertz. That's the standard that you have for the geophone, which means as you get to lower and lower frequencies beyond that, you start to lose some of the sensitivity. So that'll play into this conversation. So this shows about 20 ones, but here's actually one of the OBN arrays that we're going to look at today. This is the Amendment OBN array. And if you recognize the very south tip of Louisiana down here, this is in the Mississippi Canyon, just about 50 kilometers off to the southeast off the Mississippi Delta. And what all of these dots are actually the locations of where these OBNs were put on the seafloor by this ROV. And it's a 40 kilometer by 80 kilometer area, so a very, very large size. And what I've shown here, the color scale here is actually the bathymetry. So up here, sort of the blues, this is in sort of shallow water, 600 or so meters. And as you get down to further off down the shelf, you're down to over 2 kilometers depth. So really getting into deep water. Now we probably don't visualize what a 40 by 80 kilometer area would look like too frequently. So just to give you a reference scale that you might appreciate a little bit more, here's sort of a map of the Austin area with a 40 by 80 kilometer squared area that's outlined. So that's Bastrop in the southeast, all the way up to Lagos up in the northwest. And so just thinking about, for those of you who had the chance to go out to field school or doing seismic, think about the logistics of trying to deploy like a seismometer every square kilometer within that entire area. It's a very huge logistical challenge that companies have done. So once we have all this, the data that's put out for active source exploration, how do we think about using this data? Well, when we require the data, it's in a continuous record. And so the mindset in industry has been, let's go and find out where we had those active sources going off. Let's cut the record there. Let's grab the pressure component, the vertical component, 10 seconds around that shot point. Let's build a regular 3D seismic gather or volume that we want to actually start to image. All the other data, including the horizontal components and all the other continuous records, are kind of archived on company hard drives and not really thought of too much. So once you have this data set that then begins to look more like a standard acquisition where you tow sensors behind the boat to record, you have to go through an extensive data pre-processing and initial model building to get the background models that allow you to then start moving towards applying higher end inversion algorithms, which the goal there is to get the models you need to do really, really accurate imaging. And so one of the key ones that has emerged over the last couple of decades is full waveform inversion. This is normally done with acoustic physics. And the idea is that you have data that you've recorded. Can we come up with an Earth model that if we then numerically in the computers propagate waves through that model to simulate data, can we compare those two and actually get an excellent match? If you can do that throughout the entire volume, then you have a fairly reasonable Earth model in which to be able to do imaging. So this is what the principle of full waveform inversion is actually intended to do. So here then, once you have this, then you can do sort of an imaging thing where you think about using sort of reverse time migration, which is an industry standard imaging technology that gives you the most accurate types of images that we would expect. This is an iterative inversion process, and you can do this a number of times. Each one of these iterations is very, very expensive. And the key question is, after you go each one, you look at the convergence of where you're at in the process. Are you sufficiently accurate and do you have a good enough image that you can stop the process? Or do you have to spend a few more $100,000 going around this loop a few times? And so at some point you converge and then you can do all the high-end imaging that you particularly want. And when this works, I think it's actually spectacular. So this is an example provided by TGS, which is a Houston-based service company. And this is an area that horizontally covers 40 kilometers. In depth, it covers about 15 kilometers. And what we're looking at here is actually the superposition of two images together. So the first one, the colored image there, this is the velocity model that would come out of the inversion process. And so here we have about a kilometer at the surface, a little bit of water there, and then you start going down through the sediment package. And as you go deeper and deeper, compaction, other geologic processes, tends to speed up the seismic velocity. So that's why you see this gradient increasing with depth. At some point, you get sort of down into the basement there, and you get to the fastest velocities that you'd expect. Probably when you looked at this image, you weren't drawn initially to the background gradients, you were probably drawn to these big yellow blobs that are hanging out in the middle of the section. So these are actually salt bodies. And these are just big packages of salt, which is buoyant. So it basically has an upward buoyancy force that allows it to come up to shallow depths. So it hit barriers there near the surface and then often laterally spread out. And these are very, very seismically fast. They're very hard to see under and around because if you have something really, really fast and trying to see around that, you have to be able to have an accurate model, which can be very challenging to get for these steep salt flanks and things like that. So this is actually a fantastic job that they've done. So that's the first image. The second image is kind of a grayscale image, and that's with all of the sort of the typical seismic image that has all the discontinuities image. These are the major geologic discontinuities that have been imaged through the reflections that have come back to the OBNs, which we're recording on the seabed. So in this case, this is a nice way showing the overlap of these two, giving you a very detailed geologic and geophysical understanding of what's going on in this region. And this is just one cross-line section of actually the 3D volume. This is done over that entire 40 by 80 kilometer area. So a very, very detailed process. So those are results, but this is fairly challenging to do. From an economic perspective, this takes a lot of person hours to do all the pre-processing, building the models, working the FWI engine. It takes a lot of computational costs, so a lot of money in order to be able to compute these large-scale images. So, doing extra iterations is done only when you really, really need to. So anything you can do to try and minimize the number of times you have to go through that flow would be really, really important. So there's also a technical issue associated with this, and that sometimes we don't have sufficient data to actually even start this process. And one of the issues is that when you go from your initial model building here, if your initial models are too far away from reality, when you actually start this cycle, you won't actually converge. You'll get into local minima, you'll get the wrong answer, your images won't make sense, and you definitely don't want to make $100 million drilling decisions based on faulty imagery. And so an interesting question is, why is the data limited? This gets back to just the nature of seismic data itself. So on the left-hand side here is a typical shot gather. Doesn't really have much relevance other than to show you, if you haven't seen seismic data before, sort of what you might expect when you have a shot recorded. And on the right-hand side, this is the typical air gun spectrum. And so on the horizontal axis, this is frequencies from 0 to 250. The vertical axis is the magnitude of the signal that's recorded. And in this case, the further down you go, then the weaker that actually is. So if you look sort of the typical frequency range here, you might have sort of from 5-ish hertz, maybe out towards 100. But after that, on either side, you drop right off and you don't really have sufficient energy because the noise level, background noise level, might be, say, at minus 10 dB. So it's hard to expand the bandwidth on either side. And what we're interested in here is on this low end. So it's very, very hard to generate energy below 2 hertz, because generating energy below that means that you have to have an ever larger volume of water passing through these air guns. It's very, from an engineering perspective, hard to move that much water through the system. And so there's a natural engineering low limit on what we can do at those low frequencies. And the challenge is that the low frequencies are long wavelength, and you need long wavelengths in order to get the large-scale background architecture of your geology. So if you only have high frequencies, you're not going to be able to get that long wavelength component of your models. So what are we going to do? So industry has been working on this problem for about 20 years. They've been developing all sorts of different types of hammers to keep hitting at the problem. And maybe the problem is that we shouldn't be using a hammer, or maybe we should be looking at a different nail. So what are we actually using in this system? And so that brings me back to the OBN recordings. If 2 hertz is the lower limit that we can generate in active sources, is there actually any energy below 2 hertz that are existing in ocean-bottom nodal recordings? It might be sitting on the shelf in a data farm somewhere in a continuous record, but what is actually there that we could do? I think it's worth doing a little bit of forensics in this space to see, are we missing out on an opportunity to actually have naturally occurring 2 hertz, sub 2 hertz energy? So the way I've framed this discussion is really in 4 parts. First one is, why are we interested in low frequency ambient wave field data? In this case, ambient, just the ambient energy rattling around the Earth. What is there that we can actually use? If it's there, how can we extract that into a usable form? If we can extract it, is it sensitive to subsurface structure? We saw those large salt bodies. Can we actually sense something with this low frequency energy? And then if it is sensitive, well then what type of wave field phenomena do we observe in the data? So thinking about the first question, why low frequency ambient data? So let's go back to this image. And if you'll excuse the terrible PowerPointing, I could say, well, what happens if you take all of that away? And you're left with no active sources, but you're with a lovely, traditional waves that are just rattling around the surface. So wave energy is actually a source of ambient energy that you have nonlinear interactions that actually, when waves combine, they can actually have pressure sources on the seabed. So you can actually generate effectively seismic sources through wave-wave interactions. And so really, if we think of it, let's just look at a single node on the seafloor. It might be 100 or 200 meters below the seafloor, but sort of what type of things might it sense? And this is not something new to sort of exploration. There are those who have studied seismic oceanography for 75 years. Walter Munk had this in 1950, and what we're looking at here is on the bottom it shows two scales, the reciprocal of each other. The bottom one is the one I like to think of, so frequency in terms of hertz. So we've been thinking can't do anything below 2 hertz, so basically this here is above 2 hertz, and this is the frequency band of interest that we might be wanting to exploit in our observations. So from about 2 hertz down to 0.05 hertz. So here we have identified 75 years ago a whole range of mechanisms that can generate energy on the sea floor. So we have very shallow kind of capillary waves to these gravity waves, which are the wave-wave introductions. You can actually then have even lower frequencies, just the waves themselves, really, really long wavelength. With respect to the depth of the water, you start actually having pressure applied to the bottom. And then there's also tidal interactions and those sorts of things. So down here in this scale here, this is showing sort of the magnitude of that effect. What's really cool is that in the area where we're interested in finding energy, there's actually a huge peak, and this is the microseism energy that people have investigated. And to give you an example, here is the recordings from an ocean bottom seismometer in the Russian Arctic. This is from Antonovskaya et al., 2021. And what we have, these lines, colored lines here in the middle, these show sort of the average monthly energy that you'd expect for January, April, August, and October. And if you look here, you see, okay, in August, when there might be sort of ice-free up in the Russian Arctic, you have more energy, but then when you're in sort of the northern winter, you actually have a very low level. But here, of course, you see there's a nice sort of a bump of energy right there available. Also plotted on here are the results from Peterson 1993. Peterson was a USGS and looked at seismometers from all around the world to say, instead of just looking at one location, let's look around and get sort of collective statistics on how much energy would we expect, within sort of this frequency window. And so the lower black line here, this is the Peterson low noise model. This is the Peterson upper noise model. And so the way it's been explained to me is that 95% of the time, so 95% of seismometers around the world, you'd expect the energy regime to fall within those two bounds. Okay? So this is the data that we're actually targeting. And so the idea is that if this is the active source frequencies, can we somehow leverage this lower frequency as sort of a bandwidth extension of what we're actually trying to do? So this is the strategy that we're going to employ. Here's the second array that we're going to look at. This is the Thunder Horse array in the Gulf of Mexico. It's about a 20 kilometer by 20 kilometer block. Here we have station spacings of the order of about 300 to 400 meters, about 2,000, 2,200, I think, stations. And what's being deployed here, the color scale is just how many days this instrument was actually deployed. That red star is in the center of the array. And we can ask ourselves, let's just look at this point and see, well, what type of energy do we see? And so what we're looking at here is a spectrogram. And so on the vertical axis, this is from 0 to 4 hertz. And what we do is we take, I think, 2-minute windows, and you can compute it like a Fourier transform, look at the frequency content in that 2 minutes. You then move to the next 2 minutes, repeat. Next 2 minutes for and you do this for basically 30 hours in a row, and you concatenate them. So it gives you a measure of how the frequency structure of your data, just background ambient wavefield information, is changing over like calendar time, over this case a day and a bit. And so looking at this, a little bit of audience participation, what do you see here? Is it just white noise, or do you see anything that your eye is drawn to? I see some waves, which is probably a good thing, but what were you, so what, like where should I point to that's kind of interest? I think you were sort of pointing in this corner right up here. There's a big bright spot there, okay. Was this sort of the wavy stuff that you were pointing at to down here? Okay, that's pretty good. There's an interesting line at 2 hertz going across there, and then there's no data down there. So you identified some key points there. First one is that this is a weather event. So this is where you're recording continuously. You have a storm brew up in the Gulf that goes over your seismometer, which the storm energy actually increases the wave intensity, causing more background ambient energy. This is a sail line. So here you have a point, and you have a receiver, and you have a source boat that's going over back and forth in that Zamboni pattern. So it comes up over top and goes back and does this repeatedly. So it does this 6-ish times in this period. There's also these other things here. So this is actually, it's a 2 hertz. This is instrument noise. So this is actually a light that's turning on and off 2 times a second, that then stacking over long periods, it actually creates a coherent noise source within your record. So this is something in the optoelectronics that they probably need to look at in the design. And the other thing is that at the very bottom, around 0.25 hertz, someone turned on a cutoff and saying there's nothing useful below 0.25 hertz, let's just put in a filter to get rid of that, and they didn't actually record that. So these are just decisions, sort of hardware decisions that imprint on this particular record. Here is this other array. We can repeat the experiment. This was acquired about 6 or 7 years after, different hardware. We can repeat that experiment. Again, this is a spectrogram now, 66 hours, 2-minute windows. And looking here, it looks actually quite a bit different. There's a lot of vertical banding, so times when you have more energy sort of rattling around. But there's no 2 hertz line, which is great. But one really interesting thing is that, if you go the right way, is that we see these sort of horizontal lines. And these are, we've been initially called them Dirac combing, but these are starting at about 0.05 hertz, and they're integer multiples, so 0.05, 0.1, 0.15, 0.2. And for those of you who have played around with Fourier series, you might sort of recognize that these are sort of discrete spectra in that. So that'll appear towards the end of the talk. So hopefully I've convinced you that there is lots of low frequency energy within these single stations. So let's think about, well, how do we then take that and make it useful? And in this case, we are going to not just look at single stations, but we're going to look at station pairs. So here we have receiver A and receiver B. And in this case, we do a thought experiment. What happens if you have some sort of surface wave that is propagating along the surface that hits A, and then sometime later hits B? We don't know the absolute time when that happens, but we can probably figure out the relative time between when it hit A and when it hit B. And so this gets into interferometry, seismic interferometry, in this case by cross-correlation. So here we have, say, some random seismic source that generates a wave. We don't really care what that is, just that it actually has created energy. This little blue wave thing comes, hits A. Sometimes later, it then comes and it hits B. And so if we think about in a time series where if you go down, that's increasing time, this is illustrating that it hits at A first, sometime later it arrives at B. So what we're interested in doing is applying cross-correlation. So for those of you who have had the chance to explore what cross-correlation is, let's say you hold B constant and then you shift A, you multiply the two and you see how similar are they. You keep repeating this through the entire thing. At some point, you shift the B such that it perfectly aligns with A. You multiply them, and you get a really high value, really high cross-correlation coefficient. And that's effectively what this is that you find out by comparing these two signals what that delta T is that represents the time shift from when it arrived here to when it arrived here. So this is effectively a time lag, or delta T. This is known as an interferogram. The cool thing is that in the sort of early 2000s, this was recognized that this is sort of kinematically equivalent as if you set off an active source at A and recorded it at B. It's the same time lag between those two stations, whether it was generated at A or somewhere else and then arrived at A. It's the cross-correlation, the time difference between those, the differential that really matters. And so this is the sort of the fundamental basis of interferometry. Of course, we can switch around on the other side. We can put a source to the right. It can then hit B, go to A. We can repeat that experiment. In this case, we have to take the A and we have to now shift it backwards in time in order to get our cross-correlation. So this would give us a negative time lag. So there's the directionality, whether is this coming from the right or coming from the left, can be expressed in whether it's in the positive or negative time lags. So that's a key thing to think about in this thought experiment. Well, we don't normally have just one source going off and you call it a day. We don't control when this goes off. It's an ambient background event. In this case, you can have a bunch of signals kind of popping off on the one side. These then move from A to B, and we do the correlations, and then we stack. So we leverage the power of stacking, in this case, over up to about 80 days of just random background wavefield information. In this case, we can generate things that look like this. Of course, we go the other way from B to A. We get sort of hopefully a symmetric thing, because you'd hope that something going from A to B should be the same as going from B to A. You'd expect that from reciprocity. So that's great in sort of 1D, but reality, of course, we have receivers everywhere. So let's step up one dimension and think about 2D. So in this case, we're still going to keep A as the point we're going to cross-correlate, but now we're going to cross-correlate against a whole number of receivers. So you do this, and this is actually with field data. You do this, and you start to see, I get a lot of coherent signals. So here, this A, this at 0 kilometers, this is now offset, so offset from the point which you're correlating. Hopefully you see that there's these X's in here. Those are sort of surface waves propagating along the seabed, but then there's other waveforms that are coming in, which represents waves actually rattling around in the ocean. And the cool thing that we haven't explored much in this data set is that this was actually recording when a hurricane came over the array. And in this case, the energy regime is completely dominated by the times when the hurricane was just rattling around energy. So we have cut those out from our analysis to where we don't have hurricanes. But what we're going to do is that this then gives us the empirical seismic response. So again, this is like as if we put off an active source at time 0 here, and energy propagated outwards in an active source experiment. So these are not exactly, there's a lot of conditions that have to be satisfied for this to be the true source, the true Green's function. But in this case, we're going to call these the empirical seismic response, or virtual shot gathers, because they're not true shot gathers. So I'm going to use VSG frequently throughout this talk. So, is it sensitive to subsurface structure? We showed how we're going to extract it. We see some sort of structure in there, but what do we actually get? And let's now think in 3 dimensions. So here is back to our Thunder Horse array. And in this case, we're going to look along this sort of vertical direction here in a northern direction along the inline component. And I mentioned before that we have 4 components that you can look at in these ocean bottom receivers. We have a pressure sensor. That's what P is. So that's the first one there on the left. And the other one is the Z, or vertical component of shaking. And what you see, there's very different waveforms. On the left-hand side, right near the top of the record, these are actually P waves that are trapped within the water column. They're sort of reverberating around. On this one here, we do have those trapped modes up there in the water column, but hopefully you can see this much slower wave that's slowly transiting across the array. And the upper ones are these guided P waves, sort of a wave guide within the water layer. But then these really slow ones on the vertical are actually the fundamental Schulte wave. And a Schulte wave is a surface wave that exists between a solid and a fluid. It's basically going along that interface, and it's a dispersive wave, and basically the lower frequency components you have in that, the deeper you see. So the low frequency, see deep, the higher frequency components, see shallow. So these are Schulte waves, which have similarities with Rayleigh waves that you might have seen, or ground rule in some of your surface terrestrial seismic data. We also have the horizontal components. In this case, we have the inline horizontal component and then the cross-line horizontal component. And I think one thing that's pretty cool is that we're seeing very different structure of those waves. And that's because we don't just have a fundamental mode of surface wave, you can actually have overtones. So it's like when you play middle C on a piano, you don't just excite at 523 hertz, you actually do multiples of 523, the higher octaves. There's like a modal structure that's generated when you press middle C on a piano. Similar sort of here, that whatever's generating these waves is not just generating the fundamental mode, it's actually generating higher order modes that are arriving faster. We know they're arriving faster because they have less time it takes to get from the source point to the observation point. In addition, we're also seeing what we think are love waves. And these are waves that are going to be surface waves that are propagating transversely, and they're a little bit faster than your Schulte waves. And you see that they arrive a little bit faster here on the transverse component than the fastest Schulte waves. So we can actually see a wide variety of surface wave behavior just by taking 40 days of data, stacking it on the seafloor. Now in 3 dimensions, we deploy our instruments geographically, so we have them always hopefully oriented, north and east. But when you're a wave, you don't really care about geography. You're much more interested in being in a frame where, in this case, let's think about a cylindrical coordinate system. The waves generally propagate radially outwards. So just through data processing, we can take waves and reorient them such that we know where this source point is. Let's now reorient so we have radial components and transverse components. So we're going to now look at another movie that is a superposition of 2 images. The first we're looking at, again, this background color. This is from a velocity model, a P-wave velocity model that was independently developed by, I think, Exxon, who gave this to us. And again, the pink one here, this is now a salt body. So large salts that we know are very, very seismically fast. The gray image that we're going to look at is a wave field that is just data. So this is a data that we have correlated and stacked over 40 days, and we're going to basically interpolate this to 3D and make a movie of wave propagation. In that data, we haven't put in sort of numerically any salt bodies. It's just the data that we have recorded itself. So I'm going to play this twice. In this case, I'm going to let it play through once. You can sort of see what type of behavior, and then I will sort of talk through what our interpretations are. And this is a radial component, and this is between 0.3 and 0.8 hertz, just with the ambient field that's recorded. All right, let's go back. It plays for a minute or two, so we won't belabor the point there, but we'll come back here. And I guess I should have said that the velocity model, this is actually extracted 700 meters below the seafloor. Okay. So what happens is that the first bit of the waves that are radiating outwards, these are these guided P waves. They're the energy that's trapped in the P wave, in the water column. They don't actually see salt at all. They're not sensitive. But then what happens is you get the Schulte waves that start propagating. They get to the point where they hit the salt, and hopefully you can see they rapidly advance. They're basically speeding up their wave propagation because they have hit in the region where there's salt. So let's just play it one more time. All right, so it comes in, And then it gets to now you get the shoulder wave coming in, and hopefully you see that wave as it gets forward, it's sort of basically advancing much more rapidly than sort of the area within the sediments. Also, what's interesting is that you see here the waves actually sort of tracing the outline of the salt. So it's hopefully a fairly clear demonstration that there is significant sensitivity of these wave modes to this salt structure that's underlying 700 meters below the seafloor. But does this make sense sort of physically? And in this case, we can compute surface wave depth sensitivity curves. So this is just for full disclosure, these are for Rayleigh waves. What we're really looking at is Schulte waves, but there's pretty significant similarity between the two. And the idea here is that if you put in a VP and VS, or compressional and shear wave velocity model, such as that on the left, then you can compute for each frequency what the sensitivity of, in this case, a Rayleigh wave would be to the structure. So here at higher frequencies, so 2 hertz, you see it's really, really sensitive only to the top, say, 600 meters. But as you get to lower frequencies, you see that the depth sensitivity shifts further and further down. And we were looking between 0.3 and 0.8. So down here, you could say 0.5 is a fairly reasonable. And if you think about where that depth was extracted from that image, it's right in that sweet spot. So evidence that kind of there is sensitivity in these surface waves to larger structure. Which gets to the final point of the talk. Well, what type of wave field phenomenon do we observe? And we can look in this OBN array that we looked at before. And in this case, we can repeat this interferometry on this data set. Again, it's much larger. Instead of being 20 by 20 kilometers squared, this is now 40 by 80 kilometers squared. And we're looking at the frequency band 0.3 to 0.65. And hopefully you can be convinced that we're actually getting coherent propagation the entire length of that array. Which is pretty cool because these are, I think, 10 hertz sensors that weren't really built for this. Well, let's repeat that experiment, and let's look at 0.08 to 0.28. Sure enough, you get similar sort of thing. Waves are moving faster, though. It gets to the end before the other ones, and that's because the lower frequencies you're sensitive to deeper structure, which is faster, and so it's propagating faster. You can even go down to 0.01 and 0.8 hertz and still be able to pull out coherent wave field energy that propagates over the entire array. So, sort of really interesting that we're able to pull out this type of information. Here's a little bit higher frequency one, 0.35, and this is the pressure component. And I'm going to restart that, and I'd say just for a second, look inside of that expanding cone, and do you see anything kind of interesting? Did anyone sort of see another concentric ring forming inside that bigger ring? So that is an interesting observation that I'll come back to in just a minute. So we're now looking at lower frequencies, and we can repeat the depth sensitivity analysis. In this case, we're going quite a bit lower, and this scale now allows us to go down to about 14 or 16 kilometers, down around the ranges that we've seen. So here we're looking at sensitivities down 4, 5, and 6 kilometers in depth. And so we have waves that we've now found that are sensitive to very, very deep structures, which means that they could be an excellent candidate for building large-scale models. In this case, shear wave models, because we're really sensitive to the shear wave velocity component much more than your P wave and your density. So another thing we can do is we can say, well, 3D is beautiful, but let's now try and reduce the dimensionality. And so what I've done here is that instead of looking at all azimuths, I've stacked over all azimuths to reduce the dimensions. So the other one is now absolute offset in the horizontal axis, and we're looking at time. And I've done this for 8 different frequency windows. And what we're actually seeing is some very different structure in each one of these, a lot of these windows. So here we see, clear arrivals across the array. We see some interesting things repeating here. But we start to get up to these higher frequencies, and all of a sudden we start seeing almost like household shingling effect that's in there, which is basically indication that you have a dispersive wave mode. So this would be the vertical component, and you can repeat this for the horizontal component, or the P wave component, and get sort of similar sorts of things. So there's clearly different things going on in different frequency bands. So one way we can think about decomposing that is to compute dispersion panels. And so what we're looking at here is I've done a transform that goes from time and offset to one that we're looking at frequency and phase velocity. And so you look at this for the vertical component, and hopefully you see there's two very clear trends that are going on within the system. So in this case, we have the between B here, which sort of the low frequencies, 0.05 to 2.8, we have a nice sort of long linear feature that then is repeated. And you go to higher ones and you get sort of isolate the shingling effect that's going on. And these are because these are different wave modes that are propagating within the system. The low frequency are these Schulte waves. The high frequencies are these guided P waves that are rattling around in the water column. You can repeat this for the P wave component, the pressure component. We get sort of similar sort of thing, but in this case, we see that this energy has shifted a little bit to the left. We're actually seeing higher order modes of guided P waves that rattle around in the water layer. So it's a very useful kind of diagnostic component to see what type of energy do we have. Now, an interesting question that maybe you're asking is, why did we start seeing this repeating structure? What's causing that? We scratched our heads for a while, but then we realized that if you look at all of the shots, you can do a timing analysis to see what is the separation, the average separation between when you actually did active shooting. And here's the histogram distribution of that shot interval. And predominantly, it's sort of between 19.5 and 20.5 seconds. And if you look at the periodicity, here you see every 20 seconds, you're starting to see a repeated waveform. So this is indication that the active source energy, even though we didn't think it created any energy below 2 hertz, when you stack over 2 million shots, you take the square root of n, you have 1,000 times signal-to-noise enhancement, you actually are able to clearly see the imprint of the active source in the ambient wavefield data, which is pretty interesting because that has implications. They shoot everywhere around. On top of this, you get excellent azimuthal coverage, which means that for those of you who are really into seismic interferometry, that's helpful for being able to honor a lot of the requirements to actually having accurate seismic interferometry. All right, let's go back. The final example here, we look at this example here. So here we have one of the VSGs right in here, and this is that concentric ring that we pointed out. That's not in one of them. You can grab any of these VSGs and look in, and these crosshairs throughout the entire area are co-located. And they're at the center of what's a secondary scatterer. And an interesting question then, what is causing this scattering? And we go back to this point here and we say, well, what is located in the model? Unfortunately, someone has spent $1 million+ creating a 3D model for us to investigate. And you go back and say, well, what's at that location? And what you see is that this is the location of a salt pinnacle, sort of the highest bit of salt that happens to be hanging out within the Gulf of Mexico in this area. And where we have wave fields coming in, and it creates a secondary scatterer that then radiates energy in all directions. So another indication that there's significant sensitivity to subsurface model comment. So, key observations that we've seen. There's lots of usable 2 hertz energy that is extractable from long-time ambient records. We see coherence down to 10 millihertz. I don't normally talk about millihertz in active source seismology, but it's there. Energy sensitive to deep structure, that's within these models, and they're useful for identifying large-scale structures such as large contrast velocity, interfaces in the salt, and sort of the scattering from the shorter wavelength velocity structure. It's likely that the active source energy is contributing to this, so against all sort of normal arguments that we don't generate energy below 2 hertz, we actually do. It's just very weak, and if you stack 2 million times, you'll actually be able to do pretty well. And what we're looking at now is how do we then take this wavefield information, and develop methods that allow us to build three-dimensional velocity models that then could be useful for starting elastic full waveform reversion, hopefully also cutting out a number of cycles that you have to do of your 3D elastic modeling, which can cost up to $1 million per iteration. So let's try and save a little bit of money. So if this is of interest to you, I will be talking a little bit more about sort of a seismic specific research, what's been going on within the group, about some of the efforts we have in developing new technology that goes in that direction. So with that, thank you for your attention and happy to answer your questions.